continue with these diverse topics on process design. We talk about energy, we talk about the recirculation, and now something that is important, not for the point of view of comminution, it's regarding the liberation process when you have for example, tailing. In most of the cases, tailings has still some some valuable metals, but are not recovered. In a circuit of cleaner scavenger stage in between a grinding unit. One of them is being the vertical mill, and the other one is the ISA mill. Okay, so since you are mineral processors, what do we need? Why do we need a comminution intermediate process? All of you are familiar with that. I guess all of you are familiar. In a rotation process, you have crushing, grinding, and you have rotation. In between, you have secondary grinding. Why do we need that, Jamilatu? Why do we need a grinding in intermediate in the rotation process?
Prof, can you come again with your question? Your line is breaking.
Okay. In concentration, we have grinding to liberate. Sorry. Now again. Can you hear me, Jamilatu, again?
Yes, please.
Yeah, sorry about that. I'm saying in a concentration process, you have crushing, grinding, then flotation, and also you have an intermediate operation of grinding. How is that? Why do we need an intermediate grinding operation? Any idea from the process design point of view?
For further liberation.
Where?
Where? Okay.
Where? What stage of the circuit?
You mean the regrinding?
Yes, regrinding.
Which
yes.
is basically in the flotation circuit before going to the cleaner after the rougher and scavenger.
Okay, you have a recirculated, it depends, but usually you have it reverse grinding. Reverse grinding means first you classify and then grinding, and that goes to cleaner and then scavenger. But also in the final tailings, we have losses of the valuable elements, and in some cases you can reprocess the tailings. So the next question is, why are we losing valuable materials in the final tails? Move to Rudolf. Rudolf, if you are able to use your mic. Rudolf?
Yeah, hello, can you hear me?
Yeah, perfectly. Why we have losses of valuable elements in the tailings?
I'm not sure.
No problem. Speculate. If you answer something wrong, you learn. Okay, no problem.
Because of the fine grain size?
Okay, in the case of fine grain size, yes, the deflection of the bubble will not allow to be collected, so you have definitely irreversible losses below 10 microns. Great. That is related with the presentation that I sent you today. Okay, this is one side. What other category of material is lost in tailings? Rudolf, what other? Any idea? You can speculate, no problem with that. Rudolf? Okay, Jiru?
Yes, can it be the valuable is interlocked or something?
Very good, very good. You have a particle, and inside the particle, you have the element. Okay, so it didn't have any chance to be floated. Still, you have valuable, but inside. Okay, that's the reason, because we can use tailing, and we need to liberate. Okay, in general, coarse particles are float, all of them in rougher stage, and if any coarse particle go to flotation test, it will be liberated in regrinding. Okay, but most of the losses are fine particles and interlock very well zero minerals. For that reason, there are some plants, for example, in El Teniente, there is another plant that just treat tailings. And to treat tailings, you can use this. For example, vertimill is something really common to see in regrinding. We will see that in El Teniente. Okay, so it's a vertical big mill with the small steel balls. That's like an auger going up, spiral, like a spiral going up. And this is very interesting. The Isamil, it's at the beginning was supplied by Strata Technology. Now it's Glencore. This is very, very fine particle. The important thing is we want to have more liberated particles. If we want to treat tailings, we need to liberate. We need to have fine particles. This is possible. There is technology to reduce to 20 or 10 microns in order to liberate the interlocked material. What is the disadvantage of having two fine particles, either if you want to leach, for example, or if you want to go to flotation? What happened with the fine particles in the leaching process?
First mixing problem.
In leaching, yes. In leaching, it will increase the shear stress, so you cannot mix two fine particles. Then we come back to the ecometales process with 10% solid. What other problem we will have in flotation? They cannot be floated because the deflection lines are going to avoid the collision bubble particle. So I ask you to review the articles, presentation that I did in the conference. I'm explaining in detail flotation process because this is a broader audience, and I explain with more detail the deflection lines. Okay, so see it. I use as an example dolphins. You will see the presentation. Okay, this is comminution. Technology exists. Just to put a number in your head, to generate 30, 20 microns, you're gonna need between 30 to 40. Please write down this: 30 to 40 kilowatt hour per ton of material treated. The smaller the size, the higher the energy consumption. The larger the size, the lower the energy consumption. In a primary crusher, you will need 5 to 7 kilowatt hour per ton of mineral. But if you are going to find particles liberation or comminution, you will easily, you can get even 50 kilowatt hours per ton. Muhi, how can you explain the difference in energy consumption when you are going from primary crusher to ultra fine grinding? How can you explain that?
Did you say energy?
Yes, the specific energy required for liberation or comminution. How do you explain that?
Like first thing, I'm assuming that obviously the specific energy would be increased because of the more ultra fine grinding situation.
Actually, you're not answering. I'm talking about why.
Okay.
You're explaining, yes, more energy you need when you have fine particles. The question is why?
Because all those the attribution, collision, they need to reach out the fine particles. So it requires
More energy.
more
Okay,
energy.
no, okay. It's not like that. What about crystal?
Okay.
Another explanation, another explanation, another explanation. Crystal?
I think using the bond work index, like
Word index is a consequence of particle size. It depends on particle size. Yes, I'm telling.
in the
Primary
particle.
crusher will be 5. Ball mill combination from 3/4 inch to 200 microns, it will be 15 kilowatts.
Yes. And also the grinding time is also higher in the grinding process than the primary crushing.
We know
So more
that. We're asking why. We know that. Yes, Hernan.
Because we need more
Uh,
movement.
No. Allow me to
Oh.
explain with this piece of
I
paper.
think that
Look,
the
just
reason why also we have the energy management for the communication with the professor, I think because it became more resistant and because of increasing the surface, so it's hard to
close, Cobra, close. Allow me to show you with this following example. Look, this is a piece of paper. It cannot be tear apart, but if I make something like that, a tiny cut, see, tiny cut, tiny, see, you see there, it's a line, tiny cut, look what happened. Very easy. So you require less energy because you have a lot more cracks in the material. It contains cracks that make the detachment process easy. It's not because you are breaking mineral structure. It's because a big particle has internal cracks that reduce the energy. That reminds me an experiment we did 15 or 20 years ago, changing the blasting, the amount of material and the blasting strategy in order to introduce more cracks. We want to introduce more cracks to reduce the energy consumption in the subsequent crushing process. Understood? So when you have bigger particle, more cracks, more probability of cracks, and then the fracture occur in the particle because the mechanical strength. As you're going to smaller particle, you have more homogeneous material, you don't have cracks, and then you are tearing apart the crystalline form. Okay? Understood the phenomenology?
yes.
Okay, so that's the reason I want to ask you to review kinetic comminution against particle size, and then you will see it's linear at the beginning, parabolic, and then goes down. The kinetic, because of the mechanism. Okay, in a sack mill you have impact and it breaks because of the cracks, and when you go to fine particle size, you are going to tear apart a more homogeneous structure. So you need to keep in your mind, actually I think Luis Vinet will show you that, the relationship of K value, the velocity of comminution, kinetic, against size. You need to have that in mind. Okay, let's continue. Fine particle is good, but it will affect leaching or it will affect flotation, so we need to have another technology in order to recover fine particles, but we want to have more liberated materials. Companies are reprocessing tailings, they need to liberate because most of the material, it is occluded or interlocked in the material. That's good. That was the Giro's comment. Good comment. Okay, however, as I mentioned earlier, we will have problem with the fine particles. We already know that, the deflection, and also it's explained in the presentation that I sent to you. And the coarse particle, we explained it last week. Why do we have losses in the coarse fraction? What is the mechanism that is going on here? Rudolf, your turn. Why we're losing particles in this area when you have coarse particles?
In this case, you're talking about flotation?
Yes, it is flotation. Fine particle trace variables, yes, flotation.
In this case, the particle sizes are too big, so interactions with the bubble is not very good.
Okay, can you be more specific and more technical?
Mm.
The probability of flotation
Probability of collision?
is very good. It's very high. Probability of collision is very high. Remember, you have two mechanisms. You have two mechanisms: probability of attachment and probability of collision. And you will see that in the other document that I sent to you. It's explained in a lot of detail, these two probabilities. So again, the probability of collision in the case of fine particles, very low, and increase a lot when you have coarse particles. This is probability of collision. Probability of attachment is very high, because the particle move very slow along the bubble and has enough time to break the liquid surface. However, the probability of attachment, it will decrease when you have coarse particles, because it moves too fast. I will not have the time to break the water layer. This is called, Rudolf, this is called induction time. Induction time. So I'm doing, dear students, I'm doing this exercise, this question, not to press you, just to be trained in have a technical answer. If you have a technical answer, you will be very successful in whatever other activities, because people is not really technical. So we are repeating as many times as you are familiar with the terms and you have the understanding, okay? So in this case, we have in the coarse particle, the time when you have in contact bubble particle is not enough. The induction time to break the water layer is not enough to achieve the attachment. So then the probability of attachment goes down like this. Probability of collision goes up like this. The combined effect end up with this parabolic shape. Okay, parabolic shape. That's the reason. In order to avoid that, we have developed in Santa Maria University a carrier. So I'm asking you to study the paper that I'm referencing, to probability of collision for fine particle, probability of collision bubble particle. Please study that, because in this paper we contribute with another factor, which is the inertia of the particle, and we were able to improve a lot all the previous modeling on bubble particle collision. Remember, this is one part of the probability of flotation, probability of collision, probability of attachment, which is also explained in the PowerPoint that I sent you in detail. So we managed, understanding the mechanism, we managed to develop this carrier that changed the size. So now this 10 micron particle look like 60 micron particles, and the probability actually increased 3-4%, which is in the range for flotation. And that is really what happened. Okay, so we need to add something else to reduce the deflection of the air bubble, and we have the technologies. Okay, so now I want to talk a little bit about water. In general, of course, in the arid zones or mining area in general, we don't have water. So the alternative is to use seawater direct. This is raw seawater, raw seawater, that in general is a lot cheaper because you just need to piping for sorry, I don't have the reference here. Yeah, sorry, I don't have this paper, but this paper was done with one of my former students. This is Sebastián Herrera. Cristobal, please help me to find the paper with Sebastián Herrera from Católica del Norte University. I need to check it. It can be on Friday. Okay, sorry. Raw seawater, it can be done. Actually, Centinela mine in Chile use seawater. The only problem is the presence of chlorine. It will corrode the material, and it will generate a lot of microorganism generation. So it was a bad idea. Okay, this is the capex conveyance. It's not quite correct. It's a lot more expensive because it's different material. You require a special material to avoid corrosion. So this is not quite true. It should be a lot more, okay? And then you have the other extreme. If you go to reverse osmosis, it's too much. It's too much if you have very, very low concentration, let's say 20 microsiemens, 100 microsiemens, it will not be good for neither leaching or flotation process because it's too dilute. It will promote coalescence. Then you will have larger bubble size, and then you have a very low kinetic. Okay, so never use reverse osmosis, and not to mention it's a lot more expensive because this requires a very high pressure, 1,200 psi, and you don't need that low concentration in ions. Actually, in one plant at the beginning, they were using reverse osmosis. The concentration was 20 microns, and they didn't float because they didn't form froth. Okay, it happened that in a plant in Chile, in a VHP in Iquique is VHP. They have this cell from Goodroom, Cerro Colorado, VHP. Sorry, I'm kind of tired. I'm up from 4 a.m. So what is the best alternative? Is having a pretreatment. You don't need to have, you do use reverse osmosis, but it's not too diluted. Yes.
Please, can you go over the reason why the reverse osmosis water is not good for the flotation?
Okay, first of all, it's way too expensive. It's about $1.2 per cubic meter. It consumes a lot of energy. It consumes 3.2 kilowatt hour per cubic meter of water. Okay, and the reason why it requires too much energy is the pressure. It works at 1,200 psi. Okay, so you still can use reverse osmosis, but you don't need to have pure water. You can produce, it's important to understand, 5,000 microsiemens centimeter. 5,000, I mean, potable water will have 200, 300 microsiemens, even sometimes 20 microsiemens centimeter to drink. But this intermediate water will have 5,000 microsiemens. You cannot drink it, but it's good for flotation. You need to have some ions in order to generate small bubble and stable bubbles. If you use water without ions, you will coalesce the bubbles. We can see that if we use distilled water. Nana, I ask you to make next week an experiment with distilled water and potable water to see what happened with the bubble generation. Okay? We will see in the lab, because the best way to learn is making the experiment. Okay, Ignacio, we will use the same column that you use for the ozone, and we have TAs students hired in order to prepare the material. Okay, can you help me to gather the students? I think I have 2 or 3 more students to set up the equipment. Ignacio, can you help me on Friday to remind me that, please?
Yes, I can be there.
No, I mean to ask the TAs to do it. I'm not asking you to do it because I have TAs to do that. Okay. Two experiments.
Okay.
One will be with the methylene and ozone oxidation. Sorry, methylene blue, and also I want to see the frothing, the effect of bubble size on the quality of water. Okay, especially the still water against potable water and against water with ions. Okay, we will see that. So in short, yes, there is a good technology to, it is reverse osmosis, but producing industrial quality water, that it means 5,000 microsiemens per centimeter. And actually, the largest reverse osmosis plant doing that is owned by BHP. They process 2.5 cubic meters per second, and this is pumped 300 kilometers up to the mountains, 2,500 meters of altitude. So this engineering has been done for a huge amount and this concentration of water. So again, we don't have problem with water. Mining companies are willing to pay $5 a cubic meter. Okay, understand that? And we have the technology. Finally, I want to talk about this concept of zero waste and community impact. This is strongly dependent on the policy. We have a lot of discussion in the conference that we have here, because, for example, in US, plastic bags are not banned. I mean, you can use plastic bags, and for me, it was quite an impression. Anytime that I buy something, they give me plastic bags, and when I eat something, plastic bags, a lot of material. In the case of Chile, in 2018, it was forbidden the use of plastic bag in all supermarkets. Perhaps you are seeing that now. You need to bring your own bag, so this is happening. And Chile was the first country in America putting this regulation. Canada also started, Montreal started also in 2018, but they started using thinner or 50 microns plastic bags. And recently, in 2021, plastic bags in supermarket are completely banned. So, I mean, it's very important to having regulation, not only the willingness of the community to do it. In the same page, tires like those one, either from cars or big mining trucks, there is a specific regulation in Chile that it's called the responsibility of the producer. So let's say the Michelin, the French company which produces big tires, is responsible of taking care of the final product. We're talking about tires that cost a lot, $1 million. It's very, very expensive, the use of tires, and the company needs to take care. That was the reason with this policy that a big plant was created in Antofagasta to recycle these tires. In this case, in this plant, we will be visiting this plant not only because it's in the regard of the process design course, but also it's in San Pedro Atacama. It's a nice place to know. So this is a pilot plant that it was built by my colleague from Católica del Norte. They cut the tires and they use a process called pyrolysis, which is a process when you heat and in short you distill in a oxygen-free, no oxygen atmosphere, and you generate different materials. You generate metals, you generate different oils that can be converted in diesel. Also, you generate charcoal or black carbon that can be used for batteries too. And also, you recover the steel, the frame of the tire, that it can be recycled. This pyrolysis process was developed a long time ago. It's a German patent, and it was developed in the Second World War by German back to this time, and now it's being used a lot. not only for tires, but also for HDPE. So going for pyrolysis to convert the material, either fuel. So in this case, this fuel will be a neutral carbon, and to recover material like black powder is gonna be the motivation. And again, I want to finalize the message. If you don't have in your countries, if you have a specific regulation, you're wasting time. And as soon as you see a new regulation, for example, arsenic, we have a regulation, worldwide arsenic regulation for the concentrate, which doesn't allow us to sell concentrate with more than 0.4 ppm of arsenic. That is good, because it means we can use our technology to convert the arsenic. Okay, so this final comment was to tell you that whatever activity you do will depend on policies and environmental regulations. So taking care of that all the time. Okay, I'm done with that. We recovered many application cases, and now we're going to go to more specific topic. Since again we have, no, I think we still have time. We have 40 minutes left. The thing that I'm going to do now, I will go through all the 3 documents to explain what is the main focus, what I'm expecting you to learn, and then we will come back to the same presentations in order to see in more detail, in order for you to have more time to study. So before doing that, any comment, any question? Cristobal, you've been quiet. Any comment, any question?
Me?
Cristobal, you are Crystal.
All fine, Mr.
Cristobal, any comment? Any?
No, our screen.
Okay, you need to work on making comments. We will come back to you. And now, Crystal, you want to make a comment?
It was Cobra.
I'm sorry? Crystal?
I think it was Cobra.
Cobra, comment?
Oh, okay. No comments, but just in the case of tire, so it means that the 100% of the recovery achieved in the waste of the tire?
Not really, because you, by the way, you also generate some hydrogen and CO2 that is discharged. But of course, you can have a design when you use the hydrogen and you capture the CO2. For example, you can capture hydrogen or generate more hydrogen and capture CO2 in order to produce methanol. Okay, and yes, you could have a process design with 100% reuse of the entire tire. Okay, got that, Cobra?
Yeah.
Not to mention that the process generates a lot of heat. Okay, you're burning. Okay, now we will move again. We have 4 additional. Are you seeing this presentation? Mass transfer unit operations. Let me change the. Now I'm sharing the entire screen. So, okay, now can you see this presentation, I guess? Yes, the mass transfer?
Yes.
Yes.
Okay, so we have 0-2 mass transfer, then flotation kinetics, and then capsule on interfacial area. It's straightforward to the mass transfer, apart from let you know different operation focusing, for example, autoclave, leaching, solvent extraction, some reverse osmosis, and some adsorption. That will be the mass transfer. The important concept here, you need to review what are the concepts that we will be talking about. Those are the concepts. And it's important to understand in the mass transfer, you have phases: gas phase, liquid phase, in solvent extraction, you have liquid-liquid phase. This is the case of liquid solvent extraction. So take in consideration this slide when you have different processes and different considerations. For example, you have a solid gas phases when you are drying or using adsorption. And also in adsorption here, you can have here, solid liquid, you also can have adsorption. Adsorption works for both. You can put, for example, the same activated carbon, Nana, you can use activated carbon to accumulate butane from LPG, from the gas. Because we were seeing a presentation yesterday from a German university that is recycling lighters, the one that you use to fire a cigarette, the lighter to make a flame. And they recycled the plastic, but they didn't know what to do with the remaining gas, which is butane. So we advise, as a chemical engineer, to use adsorbent such as activated carbon. In the liquid phase, you already know you can adsorb. It's a surface process with gold. So I ask you to review carefully the different interface. Those are the operations. Okay, so that will be this chapter. Okay, and then the second chapter will be in flotation kinetics. First of all, how you can come from a batch test to a continuous test and understand that you are modeling with residence time distribution. For example, this column, this is equivalent 3 tanks, one of plug flow, and also how to connect. Look up here. You have a first order kinetic system. You have the rate of change of a concentrate is proportional to the concentration, but with this number will be K. And here you have gas velocity and bubble size. Okay, so in the case of flotation, because the Chilean track will be specialized, it will be in advanced flotation, you will learn how to connect the kinetic value with the operational variables. That we call it SB, okay? So in this case, we will test different models. It's important also to understand this part, because usually we have a single K value, but in reality, if we have a single K value, we're saying that all the particles has exactly the same size, all the particles has exactly the same liberation, all the particles have the same reaction coverage, and all the bubbles are the same. So when you put one single K value in the frequency, this is not true. You can say you have slow particles or fast particle in kinetic, or you can have a distribution like Klimpel or different shape. So we will be talking about for more precise model when you use a different model like Klimpel. In order to understand this part, you will receive a spreadsheet with different kinetic data from leaching of lithium batteries. So in order to make the best, to try fitting data, you will learn a different technology, different methodologies. This is connected with Professor Berg, experimental design. I want you to try to fit the data that I'm about to say. It's real data, okay? Understanding that this topic, kinetic, is not only for flotation, also for leaching, also for chemical reactions. So you will be understanding these fundamentals for a variety of application. Okay, those are the models. And then here I explain in detail what is the what is the induction time is explained here. We understand the probability collision. We end up, you see, with the probability of collision, attachment and collision, and we end up with the number. But you can review, and I will explain it again, okay? Let me come back to residence time distributions. The interesting thing, it's all the things that we are talking here are actual measurement from plant, okay? We measure bubble size, We measure gas velocity in industrial cell. That's the knowledge that I'm sharing with you guys. This is in Australia. Okay, this is a joke regarding the scaling up. You cannot scale up directly from a batch test. Those are pilot tests. You need to understand residence time distribution. This is very important to understand because we use this knowledge, this part, continuous reactor. Those are the models for residence time distribution. This is the actual real data from a residence time distribution for nine flotation machines in series. This is again a real residence time distribution modeling for a big flotation machine. We have 30 years experience in residence time distribution using radioactive tracers. Okay, so that is important equation. You will have a distribution of K, a distribution of residence time, and then you can use, for example, here, how to scale up from batch to continuous. Again, all this knowledge, all this understanding is not only for flotation, but also kinetic, but also chemical reactor. Okay, that will be this section, this module 3, and then we move to module 4. Module 4 is more conceptual. Let's say you have a gas reactor or even solid reactor. The interfacial area, the amount of surface that you have, the square meter of particles you have relative to the liquid phase, or the square meter of CO2 that you have in a CO2 tank to be dissolved, it depends on the size. We use solder diameter and the gas holdup. Or more generic form, it will be the volumetric fraction of the dispersed phase that will be solid, the volumetric fraction of solid, and also the particle size distribution. We like to use D32. We will be talking about distribution number, volumetric distribution, and some criteria for gas bubble system. And again, this idea of interfacial area is to improve the kinetic process. Let's say if you have a kinetic leaching process with 400 microns, you need to understand what happened with the kinetic. You need to understand the fundamental when you reduce size from 400 to 200. Or if you change this volumetric content, if you change the volumetric content of solid, you will see an effect in kinetic. And again, you need to understand the fundamentals. Okay, that is the chapter, module 4. We'll be talking about interfacial area, the technology that we have to characterize particle size, to characterize bubble size, to even characterize, this picture was taken from heap leaching. We can characterize even shape, form, and the impact that you have. You will have in September the 5th, a short course on image analysis. You will have the same numbers. I will share with you some of the codes in MATLAB in order you to take this type of picture and process and do some image analysis to determine the particle size distribution. Okay, we'll talk about solder diameter. We'll talk about the technology developed in McGill and patented by Santa Maria University and Católica del Norte in order to measure bubble size distribution. You already saw the device. You will be doing some measurement with Professor Binet of bubble size distribution and playing with the software. Okay, and using some image analysis software, we will learn this experience. And more importantly, you can determine the distributions. Okay, you see the pictures. Gas barrier, different characterization to understand the bubble hydrodynamic. It's not here, but you will understand hydrodynamic. We will go through the three-flux model. Don't be scared. There are a lot of things, but things that we have done. I mean, you don't need to develop. You will use the tools, but it's important to understand the concepts. Then we will move in this bubble hydrodynamic in this chapter of flotation kinetics and scale up. We will understand the effect of frothers, the molecular structure from frothers, how it changed the hydrodynamic, but also very important how it changed. Let me come back here. How it changed reactor. Yeah, how it changed the motion in the bubbles, because this is only aerodynamic. And this is an applied case when we change the gas injector in order to increase the surface area with very successful results. Then we'll come back to iodine, another iodine case. I'm talking about cases where we did it from lab scale, pilot test, and industrial test. So that is the beauty of that. So we did all that, scaling up from a batch test. You are going to use exactly the same reactor. Then you will see how to scale up for a pilot unit, and then the industrial design. I mean, following up all this sequence, and this was the final design, and then the engineering, okay? And again, come back to the fundamentals, interfacial error, how it's calculated. That's it, that is. So I ask you again to review all the documents and review all the associated paper with the document. You need to study a lot. You have a good opportunity to understand from the people who works on that, who develop the sensor, who develop the models, so you are with the right people to understand all of this. Okay? So that is the topic that we'll be covering. So I decided to present it in advance in order to let you to study before and understanding what are the key points here. Okay? Okay, so far so good, guys. Any comment? Okay, so I want to ask to any of you, starting from Cobra, is in the list. Cobra, what topic are you interested and what do you want to learn from the thing that I was describing? What do you want to learn? What you are expecting to learn? Cobra.
Expectation of mine is regarding
Sorry, can't
these
hear
three
you.
chapters.
Yeah, yes, for the three last chapters. What are you interested or you require to learn more? What motivates you? It can be neither. We have more topic. We haven't spoken about solvent extraction and adsorption. Do you have a specific interest?
I don't know, but the first one maybe the
Sorry?
process design and also the flotation kinetic.
Okay,
I'm not
flotation
sure about the mass
kinetic
transfer
modeling.
because
Yeah.
I don't have any background in the second one, so I don't know.
Okay, in this particular case, the mass transfer will focus in gas liquid phase mass transfer in this particular three presentation, and definitely a lot on kinetic modeling, and more importantly, kinetic scaling up. How can you go from a batch test to continuous test? Okay, Cristobal, what about you? What do you want to learn from this? Or what motivates you? What topic? Everybody will be asked.
Well,
Cristobal?
all is interesting. All the material that we see is interesting.
Prioritize.
Mm,
We have many topics, yes.
yes. Well, the energy topic is the most interesting for me.
Okay,
Ahí está el
good.
azul amarillo.
Okay.
Hi,
Crystal.
Professor. I just
Crystal.
look at this mass transfer.
Yes.
So I just thought that because it has some ethics and those stuff in. So my first priority will be the mass transfer. I will learn it, but I like
Very
it.
good. Very good. Crystal.
For me, I'm very much interested with the scaling up of like batch test to continuous reactors.
Okay. So I ask you to study more in detail residence time distribution and check the papers. Okay. We have 30-year experience as university. We are the only one in the world, Professor Janatos, doing radioactive tracers in flotation, in industrial flotation machines. So you have the right person to understand that. Okay? Hernan, I think it's not the course. You are taking the course of sustainable engineering. This is sustainable engineering design, but no problem if you join us. Same thing, you can take it. So what is it called your attention, Hernan?
the mass transfer operations.
Yes, because you don't have the course yet, but this is
Yes,
part of the course that we have. But I think
okay.
it's slightly different. So please send me an email. I'll send you the whole course that is already done. It's in Spanish, unfortunately, to you to see in more detail in advance if you have the time.
Okay, thank you.
Ignacio, what is your topic of interest? And I think you know pretty much everything.
I would like to study more in depth pretty much all the distributions, like stochastic type of variables regarding residence time and also kinetics. Like both, I think they are a little bit weak, and also the drift flux analysis. I think that's pretty
Oh,
interesting. I saw that I was tasked with using that before, and I had a mild outcome out of it. And also the scaling up. The scaling up is definitely something that I want to see.
perfect. So we're not seeing a stochastic here. We are a stochastic process. We're not using ARIMA models. This is not we not cover that. This is perhaps you're going to see that with Professor Berg in advanced process control. We do have it. We call it ARIMA model that has the stochastic component. It's a regression. It's a series modeling. Okay. Definitely drift flux. It will be very interesting to understand hydrodynamics. Then I invite you to review our latest paper, Professor Leiva and me, with a very nice update of drift flux model, considering, listen up, the effect of surfactant. So we're contributing. Actually, it's Professor Leiva's PhD thesis contributing with the effect of surfactant. Okay, and definitely for a lot of you, scaling up, I know, scaling up because it's related with design. How do you start from a batch test, leaching, solvent extraction, flotation, chemical reaction? You take this experimental data, lab scale, pilot scale, batch test, and then go to continuous reactor. Yes, this is a general weakness in engineers in general. Okay, it's very stupid the thing that all the companies, I'm talking about big companies, Hatch, I'm talking about Ausenco, for scaling up, they use a stupid factor, which is completely not has any basis because they don't know. And the good thing, companies like BHP are asking to improve that. The last consultant that I did to BHP, the big company, was exactly like that, Ignacio. Okay. So we will go deeper on that. Okay. Jamilatu, what is motivates you or call your attention? And again, it can be nothing. You can say nothing, professor. I'm interested in something different. No worries about that. Okay.
No, I
What do
was
you want to
listening.
learn?
So with the kinetic test in Olu, I think we did some models with concerning flotation. But yeah, as you said it's not for just flotation. We can also use it for leaching. Then
Yes.
yeah, so yeah, I would want to learn like pertaining to the leaching process too, and of course the scaling up of the processes too, from batch test to yeah, that's what I want to learn, and probably the interfacial area too, and the parameters that goes into it too. Yeah.
Very good. Very good. Nana?
Yeah, I've already worked on the scaling up also. There was a lot of challenge that I encountered, so I think the scaling up is very important. How you model from using a batch test to a continuous process. I would want
Yes,
to.
you are in advantage here. You are in advantage. So then you can go deeper, perhaps in using a different because you try a Klimpel model with continuous tanks in series. Okay, you remember? Then we can come back a little bit, changing the kinetic distribution model to see what happened with the equations. Okay, yeah, to scaling up. Okay, very good. Mugi. your turn to express what do you want to learn more in more detail from these three chapters.
I'm looking forward to learn more on this kinetic models. I really want to understand what really the use of those kinetic models and how to differentiate it in which situation and stuff like that. I'm really into that.
Yeah, but I think it's all the way around, Mugi. I mean, you have data, and then you choose to, let's say, try first order, Klimpel model, diffusion control model. You've been in the you've been in the Yates presentation. Yeah. Look, but once you look for the best model, then you explain the mechanism. So the model is consequence of the experimental data that tells you what is happening in the process. For example, if you are dissolving big crystals, the kinetic of this solution is going to be completely different if you have 1 micron crystals. If you compare 10 micron crystals, the curve will be completely different, because in this case it will be shrinking core model, you know. So I'm trying to say you try desperate the models, because I will show you how to do it automatically with MATLAB. It will, because you are learning fundamental, you are understanding what it means each parameter, but also you are learning data processing, which is a big advantage. Okay, you will see from you test whatever model you want, and the best fit model will tell you what is happening from the point of view of the phenomenon that is occurring. Okay, it's all the way around. It's consequence. Okay. Very good, Rudolf. Your turn. Again, from the 3 chapters, what is called your attention? What you want to learn? And again, can be nothing or okay.
Okay, for me, I agree with some other students. I think the scaling up is an interesting topic. Also, mass transfer for different unit operations. And also, you mentioned we're going to use MATLAB in some cases. I think that's would also be good, because I don't have a lot of background in that. So I'm looking forward for that.
Okay, regarding MATLAB, you don't need to study MATLAB. My advice here is learning by solving problems. We'll see, and we will provide the codes. Once you have the codes, you repeat stuff. Okay. The next time that we meet, or let's say in about 4 weeks, I'll show you how to do dynamic modeling, which is the course that is Professor Berg is doing, with a single command. You will understand a lot. I'm trying to say, you don't learn the language of programming. You learn by doing some specific code to solve some specific problems. So our focus will be in the problem itself, not the code that you need. You know what I mean? It's understanding. If you have an idea how to solve the problem, then you will have the command, and you will have the instruction to be solved in MATLAB. Okay, so start from the problem. Okay, good. Jiru, you're the last.
Yes, I'm interested in scaling up as other student, and also kinetic and mass transfer, because when I do mass balance, I feel there's a lot of things I have to consider. So
Okay, in the mass balance that you're presenting is like an inventory. It's not related with mass transfer.
yeah,
Okay.
I mean kinetic.
Okay, mass transfer is related with the velocity of how the things are being transferred. For example, I want to illustrate something. You can have milk and put the milk in a can be a pot with heated, and it will take 2 hours to convert this milk into powder. You know what I mean? You put heat, you evaporate the water, you concentrate it. It will take hours. But if you do the same milk, and you generate small droplets, 20 micron droplet, and you put it in with a hot air, it will take 5 seconds. You know what I'm trying to say? So mass transfer allow you controlling the interface and the Reynolds number, the mixing, you can move from hours to seconds. And actually you will see this equipment, which is the spray dryer, when you produce a powdered milk from fresh milk, in a residence time is 5 seconds. Okay, that is the magic of mass transfer, but you need to understand some very simple concept, and this concept can be applied for leaching, solvent extraction, adsorption, distillation, absorption, I mean any process where you transfer molecules. So my goal is to teach you the fundamentals and understanding that these fundamentals can be used for whatever operation on mass transfer, okay? So that's it. That's it, guys. Everybody spoke. I'm missing one. No, I have 9 kids this time. Yes, go ahead.
Yeah, I didn't catch what is the point of this category that we prioritize our interest for what?
To emphasize and focus the examples and the assignments. So in this case, the first assignment that you will have, you will receive a spreadsheet with kinetic results, experimental result for leaching of batteries, recycled batteries. You will have the spreadsheet. You understand?
Yeah.
The exercise is to focus the examples because it will help me for a better understanding. So I can understand from here kinetic modeling and scaling up. Okay, so we're done for now.
All of the group going to have the same topic, right? The same assignment?
Yes. Assignment, yes, the same assignments, yes, because you will collaborate each other.
Okay.
Okay, so it's time. Actually, I have 1 hour to prepare my case because I'm leaving to the airport in 1 hour and I haven't breakfast. But we made it. Thank you for your patience and happy that you joined and we didn't miss the class. So I ask you again to study deeper, check the references. You are in the right place to learn a lot of stuff. Okay, so see you. I think I'll be in Santa Maria. I think Thursday afternoon. Okay. So see you guys.
Thank
Take
you.
care.
See you, Professor.
By the
Thank
way,
you so
I met a
much.
professor from Ghana University.
Really?
I met a yes. I sent you the picture.
Okay.
She worked. Actually, it's not. She studied in. I think it's the only technology university.
University of Mines and Technology. Yeah.
Yeah, but she works for the government. She works for the government.
Okay.
And she was presenting in this conference from Ghana. So
okay.
I thought I had 2 students from Ghana. It was so good. I'll send you the picture of the just to if you know her. A picture of the business card.
Okay.
Okay, take care, guys. See you.
Bye.
Bye.
A safe trip, Professor.
Thank you.
Take care.